So yes, getting started in narrowband spectroscopy. So I'm going to be pretty informal here. We don't have too many people, so I think I encourage this to be more of a conversation. This isn't a lecture that you guys need to be quiet. If there's a question, if I'm using terms you don't know, just ask. I'd rather talk about it. So we'll be getting started in narrowband spectroscopy that lets me acquire images like you see up here on the left. I use a range of telescopes, so it was actually that telescope that acquired the image here on the left, actually in Bel Air, right behind the hospital in between Jones Junction. So you can see this stuff between all of the light pollution in the area. And that's one of the fun things about that these narrowband filters will let you do. So as a lot of you got to sit through some of our board meeting, we are a nonprofit organization. Certainly encourage membership and participation, and we'll be doing things like the public viewing out in the parking lot and in the observatory when the telescope is eventually fixed. So last August, I gave a talk on getting started in astrophotography for how things work. It's up on the YouTube channel. If you're interested in learning kind of about mounts, telescopes, and just getting started, that's a good place to go, or you can ask any of the members around here for help. I also do a lot more in-depth stuff. I'm a scientist and get to kind of tinker with all the astro tools, so I put up some of the videos on my personal projects on my YouTube channel. So a little bit about me. So I'm a chemist. I have backgrounds in chemistry and computer science, did my PhD at Penn State and all my undergrad work down in Macon, Georgia at Mercer University. So for my graduate work, I designed and built scanning tunneling microscopes. So that's actually electron microscopy, where you can image individual atoms and molecules. And now I'm kind of standing up and doing galactic level stuff. So opposite ends of microscopy to galactic cosmological imaging. And I also do a lot of terrestrial photography. And it was kind of some of that that got me into the astrophotography. If I have a lot of camera gear, saw a telescope and was like, well, that's just a long lens. Let me hook up to that and see what I can do. And that very quickly leads down a rabbit hole of all kind of gadgets and toys to play with, of which narrowband is often a favorite. So I'm going to hit a few things today. I'm going to start off with just kind of introducing what the topic is, a little bit about how it works. Is it real? Is it fake? It seems to be some of the questions that often come up, and that comes down to human vision and how we perceive the world around us. So when you actually get into the filters, there's going to be bandwidth and noise pollution that we're going to talk about. There's different filters that you can get that cost anywhere from not too much to absolutely obnoxious, more than $1,000 for a piece of glass, which gets you into quality versus cost. What are you getting when you see a $1,000 filter? And is that the one that you really want? Then there's some other details that we'll get into. Once you have the data, there's a lot of image processing to make them look nice. I'm not doing that today. I'm just going to talk about the optics part. So what is narrowband imaging? Well, that implies that there's broadband imaging. That's what everybody else is used to. So what is that? Well, it's really based on human vision. So human eyes allow us to see light in the electromagnetic spectrum, which spans all the way from radio waves to gamma waves. We can actually only see a really narrow band. But within that narrow band, there's a lot to see. So the way that our personal bio-wet detector works is that we have rods and cones, and they have certain wavelength absorbances. So a lot of the graphs I'm going to be showing today are in wavelength, generally from about 400 to 700 nanometers. That's kind of the range that our eyes can perceive photons. So you have rods, cones, rods and cones that can see your blue, green, and red. So you can actually think of your rods and cones forming like a neural network. Wait, that's the original neural network that can take sensors that see this different light and encode that into our brain in what we see as brightness, color, and saturation. So reality for us is how our eyes perceive certain photons and interpret that as color and brightness. Cameras see this world in a slightly different way. Well, first off, kind of looking at from the astronomy standpoint, how does light get to us? Well, light from the sun, only certain wavelengths reach the Earth. And so there's kind of a transmission curve is what we're going to be talking a lot about here. Or sorry, this one's opacity. So opacity means it's totally blocked. So when we get into the really short wavelength stuff, gamma rays, deep UV, those are all blocked by our atmosphere, thankfully. Otherwise, we'd be having a lot of health issues. What we see as color is this really narrow bandwidth here, and then we get into infrared and radio waves down there. Now, when you start seeing stuff from NASA about some of their space telescopes, some of those space telescopes are up there because those photons can't make it through our atmosphere at all. That's the only place you can see them, which is one of several reasons you would have space telescopes. We're going to be focusing on this little range here.
That's interesting. Even in the visible spectrum, it's still not 100% like transmission to the surface.
And that's kind of where we get sky color.
I was going to say, that's why we have blue sky. Otherwise, we'd have a reddish, purplish sky.
So we started off with eyes. They have their certain absorbance spectrums that perceive specific wavelength. Cameras do the same, but they're not quite the same as our eyes. There is a red, green, and blue sensor, but they have slightly different absorbances, and there's a whole lot of math that goes into translating what this camera sees and representing it on things like this projector and what we perceive as the right color. So the way these cameras do that is that every pixel doesn't have an RGB sensor in it. There's something called a Bel Air pattern to where you have this mixture of green, red, and blue pixels. And you end up recreating images from all of the red ones. You get a red image from the green ones. You map those onto all your pixels. So it's not just an RGB per pixel. The detector actually has a specific wavelength on each pixel that it can only detect. So it turns out cameras can see a little bit deeper into the infrared compared to eyes. I don't know if you've ever seen like a video where someone will take a remote control and shine it at the camera. You'll actually see the light flashing because the camera can see at wavelengths that our eyes can't. And that's just right at the edge of what we can perceive. Yeah.
I just point out for the visual observers, if you look at the spectrum for the eye down there, you'll see that most of the curve is over that green ring. That's why, for the smaller scopes anyway, if you go and you look at, say Orion or some of these other things, they all look kind of green, because that's what your eyes are getting. Now you get into the bigger telescopes, so 14, 15, 20-inch telescopes. They're collecting enough light so that you can pick up in the red and see breeze, but you don't see those there.
Is that also why there's twice as many greens in the Bel Air pattern than R and B?
So,
Yeah.
Any idea why we might be so sensitive to green?
Because our sun emits more green light than any other light. We actually have a green star.
And because we don't have bird eyes.
Yeah.
So all of that kind of comes together, and it really influences how we perceive color. So when you get into more scientific and professional level cameras, you don't get those Bel Air patterns. You only get a raw sensor that has no filter in front of it. And in that case, what you have to do is supply your own filters. So most of the stuff I'm going to be showing today uses the filter wheel that you see down here on the bottom. And it has a specific bandwidth of a filter for red, green, and blue light. But if you look down there, that's not red, green, and blue colored filters. It's actually cyan, magenta, and yellow, because these are dichroic interference filters. So they don't absorb light, they reflect light. So the red filter will pass the red light through and reflect everything else. And if you take white light and remove the red, you get cyan. Do the same thing with green, then you get magenta, so that you're essentially reflecting back red and green, red and blue gives you that magenta. And with the blue, you're reflecting all of this on either side except for the blue, and that's what causes the yellow. Then makes total sense. So we're kind of used to saying that RGB image, but within that red, green, blue color image, there's actually the 3 channels that you can split out into black and white images that are red, green, and blue. So I picked this shot because I have a blue shirt on. So if you look at the red channel, There's no red there, so the shirt looks black. There's kind of a mixture of a little bit of green and a lot of blue that makes the shirt. So that's kind of the mixture of that blue and green. That's what makes the shirt blue. You can see the grass here is bright in the green. It's kind of dark in blue and red because our primary color there is green. So it's about how the color gets split up in the different intensities. And when you mix them all back together, that's how you get a color image. So we can do that with an astronomical image. Here we have the Whirlpool Galaxy. And so we have some little hydrogen nebula that are in this galaxy. And if you look in the red channel, you'll see those little spots are bright. And then kind of where you have the galaxy, it's kind of darker in the red channel. Then it's easiest to compare here. We have the blue. As we go over here, you'll see that's where the blue is bright over there. So this kind of shows image deconstruction, going from what we think of as a color image to each of the individual color channels. So let me plant this as a question. What would happen if I collected a different kind of signal and then just put that in the blue channel, and a different kind of signal and put that in the green channel, and a different kind of signal and put that in the red channel, and smash them together? That's what we're going to do with narrowband imaging, is we're not going to use how our eyes work to assemble the image. We're going to use how chemistry works and physics to define red, green, and blue. So the easiest analogy here is, I think everybody's familiar with neon signs. So basically you have a gas within a tube and you excite that gas with a high voltage. So you're exciting it with between like 2 to 15 kilovolts of energy. So you're throwing electrons through that gas. Those electrons excite the atoms and molecules that are inside there, and as they relax back down to a lower state, to relax to that state, they kick out a photon. And it is a very, very specific color depending on the gas that's in there. So in this case, neon is what gives the orange, and argon is what would give the blue. So what we're going to do with narrowband filtering is exactly the same thing with nebula. We're going to think about the exact color emitted by certain gases, and we're going to build a filter around exactly how it emits. So in space, you're not applying kilovolts of energy across a gas, but instead what you have is stars that are just blasting out radiation from gamma to UV to IR, just photons everywhere. And that radiation will interact with the cloud of gas to excite the molecules just like the voltage did here. And then that gas will go through a emission process where a specific wavelength of photon will be released, and that will be specific to the gas that was in the cloud. So let's start with an emission nebula. This one is the Rosette Nebula, and I've tuned this one up so that it looks just like human vision would see it if we can see things that were actually this dim. So here we have kind of a red cloud and used our red, green, and blue filters. But what's actually going on in this object is that the red region is actually a mixture of hydrogen and sulfur gas that are emitting at very specific wavelengths, and we visually can't tell the difference between those two. They just appear as red. Then kind of in the center here, there's a region where there's a lot of oxygen that's emitting, and that kind of appears as this like teal blue-green color. And when we mix all of these together, this is what we see, kind of this red with like a whitish center. So if you could look into an eyepiece with a big enough telescope, this is what it would look like. But like I said, what was going on is that we have specific gases. These gases will have certain excitation energies. This gets into like some quantum mechanics that we're just going to say there's an energy level that you can go from 1 up to higher numbers. And if you have the energy level 3 to 2 transition, that one is called the hydrogen alpha emission. It's part of the what's known as Balmer series, which is specific to hydrogen. It has a very specific emission wavelength of 656.3, which is way out at the edge of what we can perceive with our eyes. If you had higher energy transitions, 4 to 2, you go to a shorter wavelength. So that shorter wavelength is higher energy. So it starts pushing out into that blue-green. It's out near oxygen in color. And you can also have a level 5 to 2 transition, which is even more energy at 434 nanometers, and it's getting into the blues. So these are kind of like lower probability than the hydrogen alpha emissions. So most of what we see is hydrogen alpha. This one is very weak compared to the hydrogen alpha. So the same thing happens with sulfur and oxygen. These get the name sulfur 2 and oxygen 3. Sulfur 2 corresponds to a singly ionized sulfur atom going through a similar process of energy relaxation from a higher state to a lower state. Sulfur 1 is just a neutral sulfur without any charge loss. So that was things I was having to learn, is kind of the nomenclature for how it feels like astrophysics does this a little bit differently than chemistry does. So learning that oxygen 3 is actually O2 plus. And then 10. So it's
Clear as mud, right?
yeah. So there's specific names for them. You just kind of get to learn the names and the wavelengths. But pretty much, if you're looking at any astronomy stuff, you'll just hear this referred to as hydrogen alpha, sulfur 2, and O3. So these each have very specific wavelengths.
Thank Joe for the question.
Yeah.
I was going to say, so basically, your sulfur atom has lost 1 electron. Your oxygen atom has lost 2 electrons. And that shifts where the spectrum is. That's what all that means.
It's absolutely bonkers how they figured all this stuff out, too. The history of it's awesome.
Yeah. So if you have one of the space telescopes and the really narrowband, way more narrowband filters than I have access to, NASA's done some amazing imaging where you can actually look at the specific wavelengths. So here you can see the sulfur is a smaller intensity. You get the red color here. You can actually see nitrogen that'll show up in planetary nebula. The hydrogen is very close to the nitrogen, and the oxygen that you'll see out here. You'll actually see there's different regions within the images that correspond to, that's where those gases are. And sometimes the hydrogen is not where the sulfur is. We'll get to see some of that shortly. But when you put these very specific narrowband filters on there, now you can start to identify, what are you looking at? What are the chemicals that are comprised of the nebula that you're looking at? So we kind of started out planning the question here. We're used to R, G, and B filters that are the really broad ones. What if we were to now place filters that had very narrow bandwidths that only corresponded to those hydrogen, sulfur, and oxygen? And then what we're going to do is put those into the red, green, and blue channels to represent them. So when I talk about narrowband filters, it's taking filters that are not these like 100 plus nanometer bandwidth filters here, but rather filters that are only 6 to 12 nanometers wide. So here we have the H alpha, which is that really narrow orange band. And what we're going to do with our narrowband filter is open it up so that anything plus or minus 6 nanometers to that can pass through the filter, transmit through the filter. And the 12 nanometer filter allows a little bit more through. Now, part of the importance here is in the bandwidth, you don't want it too broad because now you can let the sulfur to it. So to keep the hydrogen and sulfur, you want that kind of narrower.
Ergo, the name narrowband filters.
And we're going to get into light pollution shortly, but that's why you really want the really narrow bands. Okay, so we started with the Rosette using red, green, and blue filters. Now we're going to switch over to the hydrogen alpha and say, show me only things at the hydrogen alpha wavelength plus or minus 12 nanometers. Show me only things with the oxygen emission. And I'm going to get a black and white image there. I'm going to do that for my hydrogen, for my sulfur, hydrogen, and oxygen. I'm going to assign these to red, green, and blue, and then blend the images together. And after some additional processing, you get something that looks like on the right. So by assigning each of these narrowband filters here to a specific color, color now tells you about the chemistry of what you're looking at, as opposed to the color that our eyes would perceive.
It's kind of like paint by number with chemistry instead of paint colors.
So this one kind of comes back to something that almost frustrates me, is that reality to us is how our eyes and brains interpret the photons coming in based on how our eyes work. So is that a fake image? Like sometimes you'll hear that called a false color image. No, I'm not a big fan of that name. I really see that what we've done is we've used optical techniques to recode what color means. And if you look at it in that light, there's so much more that you can learn from these images as to what's going on. So let's actually take a closer look into the core of the Rosette Nebula. So if I've assigned sulfur, oh, there's something I should go back here. So this is what would be called a SHO palette. So the sulfur is the most red, so it gets assigned to red. Hydrogen is a little bit further, it's closer to green, so it gets pushed into green even though we perceive it as red. And the oxygen, it's kind of that greenish color, but it's the shorter wavelength, so we assign that to blue. So based on how you assign colors here, you'll see, so that's what these letters tell you. Sulfur, hydrogen, oxygen is getting assigned to red, green, and blue. You can switch it around so that it's an HSO image, so you're putting hydrogen in the red channel. So that doesn't give you wavelength perspective, but sometimes it gives you a much more pleasing image to look at. So the SHO is what's known as the Hubble palette. That's kind of one of the things that the Hubble Space Telescope did, was really establish this sulfur, hydrogen, and oxygen for the red, green, and blue. So it gets, that's where the Hubble palette name comes from. Good. So what can we say based on what I've told you here is if we think that red is a mixture or is coming from sulfur, as we look at kind of the boundary here, we can say, well, there's a lot of sulfur-rich gas out here. I did some color adjustments so that hydrogen appears a little bit more yellow as opposed to green. This tells us that there's regions out here of hydrogen. If we look really closely here, you can actually see that there's like a bubble of hydrogen that kind of extends beyond the sulfur. And we can only see this because we've recoded how the elements are appearing to us. So this is part of that recoloring that I was talking about. So in the core, all of this blue means that that's an oxygen-rich region. And then we have these little wisps of hydrogen that are just floating out there. And it's specifically hydrogen, not a mixture of hydrogen, sulfur, and oxygen necessarily, but very concentrated regions of hydrogen. So to me, this just really draws me in of like, well, how did that get there? How did this opaque dust cloud come about? Why is there like hydrogen that sits right on the surface of these dust clouds? And it's once you have the ability to separate out the chemistry through narrowband imaging that you can start to really see what's going on in these structures.
Yeah, I think it really helps you to like really define like the structure in three-dimensional space. Like the oxygen might be behind the HA, and you like see like, oh, it's like an expanding shell of hydrogen gas or something like it's coming towards you, or where they relate to each other in spatial. So it's mind-blowing.
It's very interesting to compare one of these images to what you see even through a large aperture visual telescope. You know, there's the joke in astronomy that it's a faint fuzzy, and that's honestly what most nebulae and galaxies look like. They're small, fuzzy things that are pretty much gray because our eyes can't. You know, we either don't see enough of the light to assign the color to it, and it's mostly our rods that are getting the contrast, or, you know, it's something like this where there's just wavelengths that our eyes can't see. And that's why this technique is super cool, because it takes something that we would see as just a flat gray image and makes it come alive, really. And it's much more like what it is out in space, just in colors that we can see. So really cool. So I wish I was good at it.
So just recoding color to chemistry.
Yep.
Awesome. So I've done a lot of color processing on these to make them like aesthetically pleasing and be able for us to visually see how it comes out. This has not been processed for scientific analysis. Now, that being said, the brightness and contrast here is real. This is not what's being made up. The only thing that has been shifted from reality, as we've been talking about, is what colors you're seeing. So that's where I kind of don't like the false color. I guess that's where the name kind of comes about, but I think we kind of misdirect people to make them feel like they're being deceived that this stuff isn't real, but it's just we're using color in a different way than our eyes naturally perceive.
Do you have an example of like a true HSO image, like where all the hydrogen is green?
Yeah, I have that coming up a little bit. So it's
Because it's funny looking.
yeah, yes, it is funny. You'll see why I do the aesthetic processing there. All right, so narrowband filters. So what do they do? So first off, they're going to separate the emission of different elements. They allow you to image in severe to moderate light pollution, and it lets you image during all moon phases, or at least more moon phases, because they're essentially cutting back a lot of the background interfering signal that you don't necessarily want. So this kind of imaging works on emission nebula, supernova, and some planetary nova. It does not help with reflection nebula, galaxies, except for some of the HA clouds that you can see, star clusters, comets, or dark nebula, because we're only looking at emission from particular nebula. If you're not one of those things, these filters just give you a black image. So they won't make everything better. So what they do is reject unwanted signal. That's your light pollution and broadband sources. They do not boost signal. All that they do is reduce the background. That's trickier than you think for how they work. All right, this is great. I want to do that. What do I need to go buy to make this happen? Well, there's a lot you got to think about.
Buckle up, folks.
So it depends on what kind of camera that you have. Whether you have a mono camera or an RGB camera is going to direct you down different paths. The bandwidth, usually smaller or narrower bandwidth is better, but the cost is like exponential. It goes up really fast.
Every phone's strong.
Yes.
It's logarithmic.
When do you really need smaller bandwidths? It depends on the light pollution severity. It actually also really depends a lot on the nature of your telescope. The focal ratio of your telescope will limit some of what you can do with bandwidth, and I'm going to show some demonstrations there because that's what took me forever to figure out here. I'll say it makes focusing a lot harder. While you might feel like you're eliminating a lot of that background signal, you're also going to be eliminating a lot of the star signal that lets you do things like focus. So it brings about a lot of challenges to really go to some of those extreme narrowbands. I learned the hard way about parfocal filter sets. I'll tell you what that is later. That was a hard lesson. Image sensor size. If you're shooting on a full 35 millimeter full format camera, you have to buy big filters that cost a heck of a lot more than if you have a APS-C sensor, and you can buy the small filters. So all of that leads back to cost of quality. And there's other problems that you'll run into with reflections and halos around stars that get really distracting. And if you go for the budget filters, it turns out that they're not necessarily made to the specifications you see on the box.
So to give you guys a feel, your standard DLSRs that are sold now are the APC size sensors. Full frame are more like what you expect for 35 millimeter films.
And big. There's always trade-offs. If you go more narrowband or more broadband, there's always going to be a trade-off, and you really need to spend time because these things are an investment that you really would rather only buy once.
So Brent, it sounds like you've made the mistakes to help people not make the mistakes.
Yes. I have a collection of filters, and I've sold several because I realized they weren't going to work for my setup. Okay, so I've shown this picture a couple of times. I'm going to start by talking with the H-alpha. It's going to be most of my demonstrations. Again, we're interested in the wavelength at this yellow bar. To get that, you have to allow a certain bandwidth around it, and we're going to be looking at the 6 nanometer, which is blue, and wider at 12 nanometers is some of the things we're going to be looking at. If you want to go buy these filters, you will typically find them in 12, 6, 5, and 3 nanometers. There's a whole bunch of manufacturers out there. I'll say if you want the cream of the crop, Chroma is what everybody seems to say, like they are the one and you're going to pay for it. And SB Boney just introduced in the last couple of months Some really budget ones, I think they do have a little bit of reflection, but they are the most cost-effective entry point. But you're going to have to deal with some of the complications that we'll talk about as we go. You have to pick the size that's going to be based on your image sensor, whether it's a 2-inch diameter or 1 1/4. And then if you're doing especially mono-based cameras, how they're mounted, they can either be on threaded mounts, just a piece of glass, and there's a couple other formats. You can get them in square and round, but you need to think about how you're going to be managing those. That kind of plays into camera size. I'm not going to talk about that much more, but just know as you get into the specialty mono cameras, you got to spend a lot of time figuring out the mounting. Okay, so they also cut light pollution. To know what kind of light pollution you want to cut out, you need to kind of know what's in the area. So years ago, kind of back in the 80s, almost everything was high pressure sodium lamps, those orange street lights. They have very specific wavelengths. And a few years ago, if you were getting light pollution filters, they would transmit everything and then block out the specific wavelengths for things like those high pressure sodium lamps or some of the CFL lamps that are out there. However, everybody's wanting to go to the more energy efficient LED lights now that sometimes push blue, but they're actually a broad spectrum source. Broad spectrum background is a lot harder to get rid of. We can't do these notches in the filter to get rid of them anymore. So it creates a lot more challenges, and that's one of the ways that these narrowbands try to help, is to only allow those particular emission wavelengths in that we're looking at. So this is just kind of some emission spectra of what you would get from those sodium streetlights, mercury streetlights, or the LED. Just knowing like that's what you're fighting. That signal is swamping out all your astro image. And so how do you get rid of that background?
Tell your neighbors to turn their lights off.
Okay, awesome.
Pellet gun.
So I mentioned one of the things you need to know about is what kind of camera you have is going to drive some of the filter options. So if you have a standard RGB camera like a DSLR, it's going to have a particular wavelength. And if you get some of the astro cameras, the astro cameras have a different absorbance in the red channel that allows hydrogen alpha and sulfur 2 to pass a lot more. So there's some advantages to having an astro camera. I'm going to show some demos later where I started out without an astro modded camera. That just means you're not going to get nearly as much signal through. The filter is just kind of cutting it out. When you do these one-shot color cameras, you can do something called a multi-band pass filter, where you allow multiple wavelengths to transmit, and you can have like the red channel absorb the hydrogen alpha, and the blue channel is where the oxygen will show up. So that's where you would get into multi-bands. I'll show you some demonstrations of those later. When we get into the mono, there's no filters there. It's just the quantum efficiency of how that sensor can detect photons. So it will detect like the line over there. And then it's all about what filter do you put in front of it, whether it's red, green, blue, or any of our narrowband filters. So when I first started out, I started with what was called a quad band filter with a Canon DSLR. And I was using this little 60 millimeter apo refractor. But with that combination, and in this case it was a quad band 3 nanometer filter in Bel Air, on one of the early attempts of trying to use my camera, I was able to get the Rosette Nebula, Flame Nebula, and Orion in Bel Air between Jones Junction and the hospital.
Yep.
Okay. And this is only maybe 5 hours worth of integration on a one-shot color camera.
Mm-hmm.
So there's a lot that you can do, even though standard cameras will be attenuating that hydrogen and sulfur signal.
That's a really tiny telescope.
Yeah.
It's about 2 inches in diameter.
And you can still get that.
What's interesting too, if you're doing the imaging, because cameras can collect photons so much more efficiently than our eyes, you actually want the smaller aperture so you can get more of the sky in an image, depending on what you're looking at too, which is kind of neat. It seems almost counterintuitive, you know. If you're using visual, bigger is always better.
And I think it's also that the objects that are up there are huge.
Yeah, they're
So-
very big.
So zoom is a problem because if you have a lot of zoom, and I'm going to show you later on the bigger telescope, you're only getting like this part of the image.
Yeah, you
because
see
there's so much zoom.
teeny tiny part of it.
So small is where you want to start, definitely. And sometimes like there's things you can do here that you can't do with a big telescope. Okay, so single and multiband. When I say single band pass, that's the graph I keep putting up. You only get one wavelength through. Multiband pass, Optilong has been really establishing some of the multi-pass filters. So I know it's hard to see here. This is the web resolution that they have posted, where you can get a hydrogen alpha and oxygen in the same filter. So in one shot, hydrogen goes to your red, oxygen goes to your blue, and in every shot, you're getting both of those wavelengths. And then Antlia just released a set of filters where you get the hydrogen and oxygen in one filter and the sulfur and hydrogen beta in another one. So you can do that and you get to pay the price for those. Yeah.
Oh, it hits you right in the wallet.
But if you have a one-shot color camera, I mean, those are kind of the way to go. And if you use the 1 1/4 inch, if you only have the APS-C sensor size, you can get away with the smaller filter, and that's probably half the cost.
That's actually really cool though.
So you need to think about these things as a system. It's not just that you have a filter that's going to be good. You do want to think about what is your camera doing, especially in these multi-bands. So, just do be aware. I showed success previously with a standard camera, but if you have an astro-modified camera, you're going to get a lot better images with these narrowbands and be able to see these wavelengths. But just recognize that not only is it the filter in the camera, but it's also the nature of the light pollution that you have. And there's some area, if what is around you is a bunch of sodium vapor lamps, then things will be different than if it's all the LED lights that are around. And so it really matters what's locally around you.
Mm-hmm.
So I had kind of a set of filters that were of the 12 and 6 nanometer variety. And I wanted to figure out, is it really worth it going to those shorter or to the narrower bandwidth? So I went out and started doing some testing for myself. So this is me figuring out, what do I need to do here?
And I'll grab somebody, show me some pictures.
So I'm using a Celestron 9.25 inch Schmidt Cassegrain telescope. One of the great things about this telescope is that I can configure it a whole bunch of different ways and get different focal lengths and different aperture and different f-stops. So in this configuration, the camera is on the back side. So there's a big mirror here that collects light. There's a secondary mirror in the front that reflects the light back to the camera. Really long focal length of 1,600 millimeter focal length, and the aperture to focal length ratio is f7. It's kind of a slow scope. This one was a new moon, acquired on a cold January day. It was -8 out there while I was shooting these images. It's cold. But we're going to see that this behaves very differently than what is called the hyperstar configuration, to where the light gets collected on a mirror on the back here. It then gets focused immediately onto the camera on the front side of the telescope. In this case, my focal length, using the same tube, is now 525 millimeters with an f ratio of 2.2. This thing is collecting light at a rate like 10 times faster than this configuration. So it turns out that our narrowband filters are going to behave quite differently across these scopes. Yeah.
What do I say? Telescopes like the Keck telescopes out in Hawaii are configured like that, where they have one big mirror and then they have everything going straight to the camera.
And you do not see the camera in the image. We don't have a big black spot in the middle.
Nope.
It's kind of like how when you're seeing things with your eye, you don't have the big black spot in the middle from your pupil. That's how I like to think about it.
All right, so we've seen this graph a whole lot. Only allow the H alpha through. Narrower should be better. So I'm going to acquire images using my 2 different filters here with both telescopes and see what happens. What I'm about to go through is actually like a 1-hour presentation that I did on YouTube, and we're going to shorten it into about 5 slides. So if we look at the hyperstar configuration, here we're looking at the Horsehead and Flame nebulas with the 6 nanometer filter and the 12 nanometer filter. To just look at them, you don't see much difference. There's some statistics you can run on the images to get what is called the signal to noise ratio. That's a ratio of signal versus background. It has some magic wand stuff that it waves, and it says that the signal to noise ratio for this one is 17 decibels, and this one is 19 decibels. Higher is better. Statistically, I'm not sure that that's really different. And I'm going to go in and do some more analysis on that in the next couple of slides. If I now go to my long focal length, I guess the image is going to appear there. So if we go to that configuration, now I've like zoomed in, so it's a lot narrower field of view. Calculate my signal to noise, which is actually a lot higher, but not different between the 2 filters. So why does the 6 nanometer one cost almost twice as much? We'll take a look at that in a few steps. So narrower filters don't produce more signal. What they do is reduce the background more. So if we were to look at a region that should be bright, call that region A, and a region that should be nothing but just sky glow and light pollution locally around us, we'll call that B. And I want to look at what is the contrast figure of merit between those 2. Is I would look at the intensity of the signal here and divide that by the intensity of the signal here, and that's going to give me my contrast figure of merit. We would think that the 6 nanometer one is going to have less background because it's narrower, letting fewer photons through, fewer wavelengths through, and that the 12 should be broader or lower contrast. So what I did was acquired 3 images at 500 seconds that you just saw. I do a process to register them, make sure everything is exactly lined up. And what I'm going to do is now when I do my narrowband imaging and I'm going to assign things to a color channel, instead of doing HSO, I'm going to do 6 nanometer and 12 nanometer in the red and blue channels. When I do that, that gives me a magenta image that you see over there. But what I'm going to do is extract a cross section. I'm going to say, show me the intensity of this line from the upper right to the lower left. Now we can compare what is the signal that came out of these images. So again, the red was our 12 nanometer. Blue is the 6 nanometer bandwidth. So we can see that the overall signal is lower to the 6 nanometer. It removed more of the background. And if we calculate that contrast figure of merit, we would see that we did get a slightly different answer. Now, that figure of merit depends on the intensity of the object, so we can go look at that in a few other locations. And I can also do some background calculations and show that the background was cut about in half by halving the bandwidth of the filter, and that what we're picking up here is about 0.1 photons per second of background noise, or with 6 nanometer, 0.05 photons per second. So let's now look at a slightly brighter object than what I just went through. It turns out the Flame Nebula is a little bit brighter, so I'm now going to extract a cross section here as my hyperstar. 12 nanometer gives you this higher signal compared to the blue 6 nanometer. And when we do that same ratio calculation here, it does show up as slightly higher in terms of the contrast ratio, or for the contrast figure of merit. However, if you subtract the baselines, bring that background back down to the same, it's actually really weird in this one case that you actually get different intensities. If I do that with my other telescope configuration, what ends up happening is the intensity after you've removed the background is the same at f7.
Good.
That's not how this is supposed to work. Something else is going on that took me a while to figure out. And it's something called blue shift from the angle of incidence. And this is where you need to understand how the filters work.
Go to back.
So when we talk about focal length, that's kind of the distance that you're getting where the light is going to converge. The other thing we care about is the aperture, D. And if you take the focal ratio, which is the focal length divided by the aperture in millimeters, that gives you your f-stop. From f-stop, you can calculate what that angle is, that angle theta. And as you change the f-stop, you're changing the angle that light is coming at your filter. So at f7, which is a lot slower light collection, the angle of light is actually pretty narrow. It only comes to about plus or minus 4 degrees off normal from the lens. But as we go to a really wide aperture, now the light is starting to converge in from greater angles all the way up to where I was shooting at f2.2 at about 12.8 degrees. So the challenge is that these dichroic filters that we're using, the transmittance changes with incident angle. So the way that these are constructed is that you have an optical substrate like silica or glass, and then they evaporate metals or dielectrics in many, many layers. And each layer is somewhere between lambda over 2 and lambda over 4, where lambda is your target transmission wavelength. So if that's the 652 nanometers for hydrogen alpha, you would be taking that wavelength divided by 2 and 4, and there's a mathematical process that you can go through and figure out exactly how to stack all of these layers so that that wavelength will go through, and it will have a certain bandwidth that gets either transmitted or rejected. So with these particular materials, remember I said that there is a dichroic interference filter. What happens is if you interfere with these in the wrong way, you get reflected back out. If you interfere with them the right way, you transmit. And it's all dependent on the thickness of all of these layers. If you change the angle of incidence of the light into that filter, you change the apparent thickness of each of those layers. And it turns out that the steeper that layer that the incident photon is, it'll have the effect of blue shifting the filter. So what was transmitting 656 will now start transmitting 657, 658, 659, the steeper the angle. So this is where it's important to recall. This is a batch manufacturing process. Someone is having to physically make these things. Cheap filters may not have the same quality control that more expensive filters do, like the precision with exactly how thick each of those layers is. As a result, the bandwidth may not be what it says on the box, and the transmission peak frequency might be off. They may have just had a bad batch, and it transmits at 660 instead of 652, and all you see is black. And there's been a lot of that where you see people complaining about that on YouTube and different places to where they'll go back and say, no, this was a bad batch of filters. But it took a lot of work to figure that out. So that's part of what you're paying for with expensive filters, is the guarantee that you're getting what the box says. And a lot of these are also kind of delicate, so a lot of the newer filters I also want to see that they indicate they're putting kind of a hardened layer on top that won't scratch or mildew over time, since these things are out in the weather quite a bit. Okay, so approximate shift in wavelength. So if we look at the incident angle, I was telling you at f2.2, it's coming in at 12.8 degrees. That results in a 3.8 nanometer shift. So if you're a photon, you're coming straight in, your transmission is going to look like this. So if you're an H alpha photon coming in, you're going to transmit no problem. But if you're coming in on an angle at 12.8 degrees, because now each of those layers feels a little bit thicker, it's as though that transmission shifted over, and now you're halfway down that transmission peak. So all the photons that are over there, you're actually attenuating because they're coming in at such a sharp angle. So after searching and reading for a while, there was someone that had been doing a optical physics project, and they actually wrote some Python code that does the ray tracing. I was able to modify that Python script a little bit and change the inputs so that I can ask the question, where are the photons coming from? And in my long wavelength, or my long focal length edge scope configured for f7, what this is telling us is that photons start coming in at about like 1 point something degrees. Most all of the photons are then going to have an incident angle of less than 5. For my hyperstar, and again, there's a so all of the Schmidt-Cassegrain telescope that I'm using has a central obstruction. That means that there are no photons coming in at the 0 angle. They're all coming in kind of with that central obstruction blocked. As we go to the hyperstar, more of the photons are coming in at these incident angles. And if we look at this incident angle compared to the transmission of the filter at that incident angle, we can see that for the 6 nanometer narrow bandwidth filter, where most of the photons are coming in, we're only getting like 50% transmission. So the reason that I was having that weird signal with the hyperstar is because of all the high angle of incident photons being attenuated because the filter had become blue shifted because of that angle. So if I go to a 12 nanometer bandwidth filter, now I'm not going to have that issue where I have as much attenuation, but I'm not removing as much background. So it's where you get to balance things out. This happens for lenses as well. So here I'm showing a Samyang 135 millimeter lens that is at f2. So here you don't have a central obstruction, so you do have photons coming straight into the filter. Most of them are at about 6 degrees, but a lot of this area out here is at longer wavelengths, so you're ending up throwing away a lot of your photons if you're using that narrower filter.
So that seems counterintuitive to me. Is it just specifically because of like the coatings or how they're put on, or like you almost feel like if it was coming in a more narrow channel, you would get more signal instead of the other way around, or more clear signal than the other way
It
around.
has to do with the angle of incidence on the equations that he had up there.
Right. So what's causing that though? Is it
So you come in if you come in at a shallow enough angle, everything will be reflected and nothing will be transmitted.
it's almost like coming into the atmosphere? Then like
Exactly.
actually it's exactly like coming into the atmosphere.
That's exactly what it is. It has to do with that. So like it's in the diamond ring, why it sparkles. It's because it'll come in and then it bounces around inside until it gets the right angle to come back out.
Yeah. There's no way I would have figured that out.
And so I have a degree in chemistry. I've done a lot of this stuff. I had to spend hours reading through Cloudy Nights and reading up on how stuff worked to be like, oh, this is what's going on, and then finding the physics of how dichroic interference filters work and stuff. So I mean, it's
Gotta be so gratifying though. Like when you figure that out.
I mean, to me, that's part of the satisfaction of doing the astrophotography. Is it creates numerous projects to where you have to go learn stuff. And once you do, you've kind of mastered another topic that's another tool in your toolbox to solve problems.
And then you can pass it on to people.
Yeah. And you get to make pretty pictures. That too. So what can I say about fast optics? There's a whole lot of data that I didn't show, and basically it kind of turns out that the more light polluted the skies are, the more effective the filters become. And where I was testing, I was in like about a Bortle 5 to Bortle 6 zone is where it's what the maps said that I'm at in Bel Air, believe that or not.
Rick Jones, I totally believe.
If you were in a more light polluted location, you would be seeing a lot bigger differences between these 6 and 12 nanometer filters. But that also says if you're at a dark sky site, kind of don't need these things.
Yeah, the solution is to go to a dark side.
I mean, that you can buy cheap.
Yeah, like live in the mountains, most cost-effective solution.
If your telescope is f4 or smaller, you need to be aware of that as you select your narrowband filters. There's a lot that goes into that. There are specific filters out there that are called fast optic shifted or high-speed filters. So Beta and Chroma have some of those. They seem to work pretty well. I'll say one challenge, though, is the ones that I have at 12 nanometers, I can use those on any telescope. These high-speed filters, they must be used on these high-speed scopes only, usually with a central obstruction. And they are crazy expensive. Aperture costs you everywhere. So one of the next things I learned the hard way was back focus. So back focus is the specific distance from the last optical element in your telescope to your camera sensor. If your camera sensor is too close, they'll have good stars in the center, and they will start to have these outward-facing streaks in the corner. If you're to adjust the camera a little bit, then it becomes too far away, now you have radial streaks as opposed to the points. So when you get it just right, everything will appear as points and stars. And while they say 55 millimeters, it might be 54 point something for your telescope and 56 point something for somebody else's telescope. So you got to play with it and tune it up to figure out what works for your particular setup. This becomes more critical the larger the smaller your f-stop. So if you're, again, less than f4, the accuracy with which you have to get the back focus, this becomes more and more critical. I use shims that are down to like 0.05, 0.01 millimeter increments to get mine fine-tuned. The thing is, that back focus assumes that the material you're transmitting through is air. If you introduce a new material, like glass, the back focus changes. So if you have your Rosette telescope and you put your DSLR camera or your Astro camera up there that's RGB, and you tune it up without any filter in there, and you get that back focus dialed in until it's perfect, and then you put a narrowband filter in there, your back focus will be off, because now you're pushing the light through that optic. It has an index of refraction that is different than air, and now your back focus is off. The way I figured out how to do this is with my RGB camera. I would use a luminance filter that's made by the same manufacturer as the narrowband filter. That would give me the same back focus no matter what filter I was shooting with. And that was one of the hard lessons, is that I got some nice astronomic narrowband filters and had some ZWO RGB filters, and then realized every time I wanted to switch out, you need a different back focus, and to do a different back focus, you have to take your telescope apart, put shims in, and then screw it back together. That's not fun. So the thing you want to do is look for filter sets from a given manufacturer. Make sure that you'll sometimes see them called parfocal. That means that they have the exact same optical characteristics in all the filters, so you don't have to tune the back focus for each filter that you own. That took a while to figure out.
Yes.
So then, is there a way you could, like, instead of just doing trial and error and like putting in like 0.05 millimeter shims, could you like plug in an equation and be like, okay, I need to have exactly 55 millimeters between my filter and my sensor? Or is it just really trial and error, and depending on like how well it was manufactured?
So I think the manufacturing tolerances is really the
dominant
thing. Yeah. But I'm actually working on a tool right now that I call a back focus manager, because I like to tinker with my telescopes. So I'm always switching out cameras and optics and other stuff, but then I need to know, for this configuration, I needed this exact shim thing, so I don't have to spend half of a night getting my back focus right for that configuration. So once you get it, write it down. Yeah. So one of the other things narrowband filters do is they influence star intensity in your image. Usually if you're narrowband imaging, you're interested in a nebula, but it also influences star intensity. So basically here, I was seeing that the 6 nanometer filter reduced star intensity by a factor of about 2 for most of the stars I was looking at. So a lot of times when you're doing nebula imaging, the stars end up kind of distracting you from the actual nebula. So it's kind of nice to have stars reduced, especially if you do it at the optic level. Now, that doesn't always work out the way you would think, because not all stars emit at the same wavelengths. So depending upon the height of star that you have, it will emit at different wavelengths. And what we're doing is putting a narrowband filter on top of this profile. So if you're a B-class star that's mostly blue, it's not going to appear in your H-alpha image. If it's in some of these mid-range stars, it will, and as you go into the class M's, there'll be only some tails over here. So some stars will be attenuated more than others for each filter that you use. That leads to the next problem, that when you go back to recombine these, the stars, so here is the image that Tim was asking about. If I do a straight up HSO image combination, SHO, so sulfur, hydrogen, oxygen, the hydrogen appears green, and that's why this one looks green. But I've now taken the red of sulfur and the red of hydrogen, and I've taken that hydrogen red and assigned it to be green. And I've taken that teal of blue of oxygen and assigned it to blue. As a result, as opposed to having nice kind of white to orange stars, they're now all have these magenta colors. So that's pretty common with narrowband images. There's software things that you can do, or one of the things that I do is I go back and get RGB images, and then I use the RGB image for my star colors. And that's a lot more work, a lot more time, but you don't get the magenta stars, which I don't like to see. That's personal stuff. So if you don't buy magenta stars, then you don't have to worry about it.
Scientists don't care.
Yeah, it's
So they're just collecting to get that image so they can tell where the hydrogen, where the oxygen were, and they don't care about star colors.
So how are we doing on time? I need to speed this up. The filters can cause reflections. I'll just say, so this is Alnitak. It is a really bright star, and it can cause reflections. And we're going to look briefly at some of those reflections. The halos are different between the telescope configurations, partly due to the focal ratio, is where that kind of shows up. When we look at oxygen, we'll just look over here at this one. There was some really big reflections that show up there. They get kind of distracting. A lot of people blame the narrowband filter as being the source of the reflection. And it turns out, if you know the diameter of the reflection on the image in pixels, and you know the pixel pitch of your camera, how many microns per pixel, you do some unit conversion, you can figure out how big that little reflection was in reality. How many millimeters was it? If you take that physical dimension, multiply it by your focal ratio, you can figure out the distance that the reflection originated from the sensor. So if you start looking at all of the objects between the filter, the anti-glare, anti-reflective window, and the camera, there's some other stuff down at the sensor, you can actually go back and figure out what is causing the reflection that was the problem. So I went through and did this for sulfur and oxygen, different wavelengths, and you can actually see that it's some reflections bouncing around different parts of the camera at different wavelengths, not necessarily the filter that was causing the problem. You can see my YouTube video because that takes like an extra 15 minutes to explain, and we need to get outside pretty soon. One of the other things that I came to appreciate is camera sensors are not just a flat plane of silicon. They actually have what's called micro lenses on top of them. So there's these little spherical lenses that allow more photons to get captured per pixel. So there's a wider acceptance angle because that angle of incidence matters at the sensor as to whether the photon gets detected. So these little spherical caps help you collect more photon. The thing is, if you put a really bright light in there that looks kind of like a star, and it hits those little micro lenses, it will cause diffraction. And if I look in this image and I filter back, you'll see there's actually a diffraction pattern, if you look in the image, that's caused by one star hitting a few of those micro lenses, creating a diffraction image that reflects off of the anti-reflective window and back down on the sensor that's causing all of these halos. So that's not the filter's problem, that's a characteristic of the camera that you only see when you put a narrowband filter in. There's some other fringing stuff that goes on, and in this case, the fringing, these kind of like little wave patterns, they're wavelength dependent, depending on whether you're doing the hydrogen or the sulfur. turns out that there's a little cover slip over the sensor, and what was causing all of this is reflections between the micro lenses and the cover slip right over the chip. So there's all kind of little things that are going on that can cause these image defects, and it's not just blaming the expensive filter that you buy. So halos kind of depends on the wavelength of the filter that you're looking at, and other parts of your optical system can cause the issues. Star reduction, narrower bandwidth will reduce the star intensity more. For contrast, I was saying contrast figure of merit improvement at f7. However, at the fast optics, I was actually seeing attenuation for the narrower filter, so you were fighting background removal with attenuation, and that wasn't necessarily a winning situation. So when I shoot on my Hyperstar, I use 12 nanometer filters. When I shoot on my f7 scope, I'm using the narrower filters. So what can you do with this? So here we're looking at the Cigar Galaxy. This is an RGB image where I've also acquired HA signal. You can actually see these hydrogen alpha jets emitting from the core of this particular galaxy, so you can mix narrowband with broadband to get these kind of images. This is the Elephant Trunk Nebula where I did HSO. This was on the Hyperstar, and I brought in, again, the RGB stars to make it look pretty. And this is a case of HSO as opposed to SHO. It just looks so much prettier with the hydrogen in the red channel when I worked it up. I tried it both ways. That one just looked way better. And then this is the Rosette Nebula. This was a 2-panel mosaic with the Hyperstar, also in a HSO palette. So you can generate really pretty pictures with a narrowband. It's a lot of fun. And you can do it in light polluted skies. Yeah, we'll skip over that one since we're late on time. So selecting the right filters, we've hit a lot of the topics. You can get multi-band or single pass filters. You need to think about your light pollution, the type of camera that you have, and just be aware that the narrower filters come with difficulty costs. Be aware of parfocal filter sets. Try to get them all from the same place. It'll make your life a lot better. Your camera size is going to make a huge difference, and whether you need the big filters or the small ones, so that's a huge cost driver. So go with as small as you possibly can. Be aware that the cheap filters come at a price, which is usually your frustration. So I've bought several things trying to be economical and had to sell them and get new things. So I say buy once, cry once, just invest in quality. You end up saving money in the long run if you're going to actually do this. So
You need to get that on a t-shirt. Astrophotography, buy once, cry once.
So just be ready for lots of image processing and make sure you're aware of all these trade-offs as you invest in the filters. And for all the frustration that I've expressed here, it is a lot of fun and really satisfying to do these images. So thank you. Happy to take any questions before we head outside. Bye.
You've got one.
The same economics that you talk about for filters applies to eyepieces.
Yeah, it really does. It really does. It applies to everything in astronomy, really. But, again, you're doing this, and we'll have this on the YouTube channel. It's so that other people don't have to do all the trial and error that has already been done. You can take some of these tips and tricks and hopefully have a less costly adventure in astro imaging. What?
No.
What's costly?
So I think the thing
I
is,
said less costly, not costly.
build up over time.
Yeah.
Then you can go and take images. It's just focus on this talk was the narrowband imaging. From an imaging standpoint, this is kind of like the mountaintop. Right? You can take your DSLR and put it on your back of your camera and shoot something without filters, without anything.
Or your
something
iPhone.
pretty cool to look at, or your iPhone, right? And get something pretty cool to look at and show your friends and family. And that's kind of the way we all get started. Like, you know, wow, that looks good on the eyepiece. Can I hold my iPhone up, look at the picture? Well, not that steady. You know. And then you say, well, maybe if I get a little camera and stick it in there. Okay, that works. And you play with that for a while, and then you learn. And as you learn, say, okay, I'm good to this point. What do I need to get better? And as I go to the next, and right. And then the narrowband imaging stuff is really kind of the top end of stuff. And that's really, really, really good at this.
And I had to learn all of this kind of during COVID, and I didn't know this group existed, so I was doing all this. So for anybody that's new here, like that's what the group can help you with, is figuring this stuff out.
And you don't have to start at the mountain.
Yeah.
Yeah.
But
But we have a path to get you there if you want to go.
it definitely, you definitely get some of the most beautiful pictures kind of putting in that level of effort and investment. You know, to Joe's point, it's really, what are you trying to get out of it? Do you just want to have something that's kind of cool to show your friends, or do you really want to make something that is very aesthetically pleasing and, you know, quite frankly, a work of art, you know? So you don't have to always make a work of art. You don't have to be Da Vinci every time, you know, but you can get there if you want.
And I'll say, as I've gotten into this, I appreciate more and more the visual aspect. I mean, like this can become work if you let it become that. It can be kind of a chore, and it can become frustrating to get what you're hoping to get. But it's really nice to just take a telescope out, point it at something, and get a look at it.
Take a look.
And go do 5 or 6 objects in a night, where I'm doing 1 object in a month on this kind of stuff.
It's really fun, like, especially you can get like multi-band filters for not crazy prices, and you're able to see like a lot fainter nebula than you would ever be able to see, even with like a 10 to 20 minute of exposure. Like you can see that in 2 or 3 with a multi-band filter, and so it's really great.
Yeah, and again, that's with the multi-band filters. You don't always have to, you know, invest all the hours and, you know. So there's definitely a lot out there.
All right, is it time to get outside?
I think so. Okay. Thank you, Brent.
You say?
I'm going to go ahead and end the recording. Thank you, Stephen, for hanging around. Dr. Chick.
Clear.
Yeah.